So we can do engineer's induction and assume from the previous discussion that now we know how to evaluate expressions, right? So actually the expressions are conceptually confusing sometimes, a lot of the times, because they actually do have this recursive structure that throws people off. Statements are quite a bit easier, but we'll get to statements in a bit. Function calls and function returns are tricky because they actually involve a handoff between two different parts of the program, two different functions, and the compiler is only doing them one at a time. Right? We're compiling these things a function at a time, which means that we have to be careful that we set up the code properly so that the caller and the callee interact as expected, despite the fact that we don't actually have both the caller and the callee around at the same time. We're generating code for the caller. We may not have seen the callee yet. So we have this notion of the calling sequence and the standard calling convention. And what we'll be doing is, at the caller's end, here's what needs to happen at runtime. The caller needs to evaluate the actuals, place them at the appropriate location, and then save some machine state and transfer control to the callee. So this is what the caller needs to do. The callee needs, when control reaches the callee, needs to allocate the activation record, save any registers that may need to be saved, update the pointers and so on, and then start executing the body. Okay. So the intermediate code instructions for evaluating an actual parameter and placing it on in the appropriate location is a param instruction. So X is, in this case, and I forget what the 3-address instruction is in the set that I gave you, but if it's not this, it's something very similar to this. Okay? And this says that this X, which is a pointer to a symbol table entry, is the kth actual parameter of the call. And then save machine state and transfer control is simply call this guy, call the callee. Callee has this enter instruction pointer to the callee's stack frame that says allocate this much space. And the amount of space that needs to be allocated is in the assembly code, the MIPS assembly code you'll generate. And that's going to be computed by traversing P's local symbol table to figure out how much space you need. One thing that I want to mention, because that document about translating 3-address instructions to MIPS assembly, unfortunately, is very confusing on this part. And since I wrote it, I feel bad that I wrote it in a confusing way. There is all kinds of verbiage in there about saving callee saved registers as needed. Okay, so that's the general case. In general, a calling convention will say, here's a bunch of registers that the callee has to save if it's going to mess with them. For your project, you don't have any callee save registers. Okay? And the reason is that all of our variables live in memory. Okay, so their permanent home is in memory. They get loaded into registers in order to get evaluated for arithmetic, and then they get put back into memory. So what for your project purposes, you should hash define save callee save registers to be empty. All right, that just nulls out. Here's what I mean. There's this documentation. There's the translating 3-address code. Come on. And it talks about how to translate a call and enter instruction. Here we go. Enter. Set up the frame pointer. Save the registers that need to be saved. So for you guys, you need to save the old frame pointer and no, okay, for you guys, here, save the old frame pointer and the return address, that's it. You don't have to deal with callee save registers because the code that you're generating doesn't need to worry about them. Okay? So just please remember that. This is a simple situation. You don't have to deal with callee save. If you do save the registers, that's okay. It's not necessary. Okay, so save the frame pointer, save the return address, and you're good. So this is what your code looks like. Save old frame pointer, save return address, set up the frame pointer, and update the stack pointer. You do not need to do this part. You don't need to save each register used by the procedure because it doesn't matter. Steve? Could you speak up, please?
Yeah, it doesn't matter because it's all kept in memory.
It doesn't matter because all the variables are being kept in memory. The reason you need to save registers and restore them is that, okay, that only applies to registers whose values need to be consistent across the caller and the callee. Okay, so the caller has certain things in certain registers. The caller makes a function call. If the callee messes up the register, it doesn't clean up, and then controls comes back to the caller, and the caller says, okay, you messed up my registers. That's not good. Okay, so that's the reason you might want to save registers. So the callee says, well, I'm going to be a good citizen. If I mess with any of some set of registers, I will save them ahead of time, do whatever I need to do with the registers, then put the saved values back so the caller is not affected. Okay, that's the reason for the save restore. In our case, the only registers that need to be preserved in this manner are the frame pointer and the return address register. That's it. Therefore, we only save those two. The caller doesn't care about other registers getting messed up because variables are not stored in registers. They're always stored in memory. Okay, so we'll temporarily retrieve them into registers for arithmetic, but we'll always put them back. Therefore, we don't need to mess with other registers, just the frame pointer and the return address. Now, John, you had a question?
I'm still working.
Okay. So if I talk really, really quickly, I'll get to the end of the class before he works it out. Then I won't have to think. Function returns. What the function return does is it restores the callee save registers, but you don't have to do that. The reason I keep mentioning it is that there's a distinction between what you have to do for the project and what additional things you'd have to do if you had a lot more time and we were building a more sophisticated compiler. And if you had a lot more time, then we would be restoring callee save registers. If there's a return value, put it where the caller can find it. That's dictated by the standard calling and return convention. Update stack and frame pointers, so deallocate the stack frame and then return. And the caller, when control returns from the callee, unless you're dealing with a void function, there's a return value. Okay, so the caller needs to get that return value and do something with it. Now, the exact location where that return value is going to be will depend in part on the calling convention, in part on the language that's being used, possibly on the architecture. Okay, so on the MIPS architecture, the return value might be placed in one register. If it's an integer value, if it's a floating point value, it might be placed in a different place. Floating point values typically don't go into integer registers. On the Intel architecture, x86, there'd be a different register. Obviously, the register conventions are number and names are different. At the intermediate code level, you want to abstract away from that level of machine-specific detail. So we'll say, you know what? There is some location where the return value is placed by the callee, and the caller knows what that location is because there's a standard convention that allows us to, the caller and the callee to communicate. The exact location depends on the type of the return value, on the calling convention, on the architecture, and so on. So let's not commit to where exactly that one is at the intermediate code level. We'll simply say, hey, wherever that value is, go get it and put it into X. So at the intermediate code level, the retrieving the return value is retrieve the return value from wherever it is, which is implicit, and put it into X. What is X here? X is a symbol table entry. So the retrieve instruction says, get that return value, stick it into this location, now I'm ready to go. Because now I can take that symbol table entry and work with it just like any other variable. Okay? Yeah.
That worked out.
Okay.
If you have like a recursive function though,
Mm-hmm.
and you're not storing the temporary variables that you're using for passing a reference to say the function is going back into itself, is it going to lose its reference?
Ask me the question again, I'm sorry.
Okay, if you have a recursive function,
Uh-huh.
okay, that has say a parameter, some x or something that's an integer, right?
Uh-huh.
Well, normally I remember when I took this, you basically you pass a temporary variable, but you're storing it in the stack frame.
Mm-hmm.
And then you restore it when it comes back to the function as it's unwinding. But if it's going into the function and you're using, say, a temp register for holding the value, so you're passing the function, isn't it going to get wiped out when it comes back?
Yeah, how do we deal with recursive functions? Again, in our case, variables, local variables, will always live in memory.
Yeah, I know, but you're passing a reference though, or some reference.
Okay, so
space or something.
fine. So let's work through this. For a second, just hold the thought on the reference. Let's just deal with the situation where I just have the variable, and then I'll come back to the reference issue. So suppose I have something like a simple Fibonacci computation. So I have a local variable x, and I'm going to, local variable n, which is in my stack frame. I compute n minus 1. I create a temporary to compute n minus 1. I compute n minus 2. I create a temporary, and I pass those values into the recursive call, right? So call by, this is in C, it's called by value. I create a copy of that value, and I give it to the recursive call. Okay. So all of these, the temp for computing n minus 1 and n minus 2, these are temps. They live in my stack frame. Okay. So now I make the recursive call. I take the actual argument, the value of n minus 1, say, and I put it wherever. I put it where the callee can find it. So I put it in maybe a register, maybe on the stack, whatever. Then I make the recursive call. The recursion works. It comes back with its return value, and I retrieve that value and I work with it. So okay, so far? Okay. So now let's suppose I have pointers in my language, so I want to do a reference. So let's suppose, just for grins, that what I'm going to be doing is passing a pointer to the location that holds n minus 1. So that location is in my stack frame, right? So I compute the address, and I copy that address, and I give it to the callee. So I take the address, and I give it to the callee. Okay. So the callee now has this address, and it's doing whatever it needs to do, right? So now the callee returns. Whatever changes the callee wanted to make through that pointer, it has made already. So the callee's copy of that address, of that argument, the argument that was given to the callee was placed in some location. Maybe this is on the stack, or maybe it's in a register, but it was placed in some location where the callee could get it and work with it. Now that location has gone away because the callee stack frame got deallocated through here, right? But that's okay because the callee, because it had a pointer, was able to make the changes in my stack frame that it wanted to. Does that help? Not really. So your question earlier was, won't we lose the reference? Right? That was your question.
Yeah.
So when we return, so you're right. I make the function call. So again, let's think of recursive Fibonacci. So I make the recursive call. I give it maybe I give it a reference to one of my local variables, or I give it the value of my local variable, whatever. But the value that is passed into the callee is in fact a local variable in the callee stack frame, right? Because the formal parameters are locals. So therefore, when the callee returns, that whole stack frame goes away. The activation record goes away. So the local variable is gone. So you're absolutely correct about that. If my program depends on my having that local variable, being able to access that local variable after the callee has returned, then I have a problem. So because it's gone away. Therefore, if your language allows static locals, then the compiler has to spot that and say, oh, look, this is a local, but it's static. I need its value to stay around, and it has to do, it can't allocate that on the stack because the stack is going to go away. If it's not a static, if they're automatic variables, then they will go away, and that's life. If I, for example, if the callee returns a reference to one of its locals, that's a dangling pointer. Does that help?
Well,
No, have I confused you even more?
But I'm not really sure if that really solves the problem.
Mm-hmm.
So can we just, instead of dealing with actually passing integers, we could just always pass a pointer so that the thing that gets changed happens in the caller?
So the observation is that if instead of passing an integer, I could always pass a pointer. So in programming language terms, you would say that instead of passing things by value, I could pass things by reference. And whether or not that is legal depends on the language. Okay, so if the language specifies that, you know, what happens when you make a function call, if it allows you to pass things by reference, then yes, you can. And I guess what I'm saying is a truism. If the language says you can't, then you can't. But my point in making this fairly obvious statement is that there are programs where passing by value will give you a different result than passing by reference. And this used to be, a long time ago, they had these exams for the PhD qualifying exams. And a perennial favorite was, here's a program. Explain what, show what gets printed out if parameters are passed by value. Show what gets printed out if parameters are passed by reference. Show what gets printed out if parameters are passed by value result. So all the various parameter passing conventions. We don't do that anymore. So let me talk a little bit more about function calls. What I'd like to do, because discussing functions and function calls and code generation for functions is important, and it's going to be important for your project, what I'd like to do is have Sam talk about code generation on Friday. So essentially, pick up where I'm going to be leaving off, instead of focusing on project-related discussion. Okay, so just FYI. So here's a little function call here. Okay, so this function f takes two arguments, 0 and y plus 1, makes the call, comes back, takes the result, adds 1, stores that into f. Okay, so here's what your intermediate code might look like. At the caller's end, I have to compute the sum y plus 1. I'm simplifying over here because I needed space. But if you think of our earlier discussion about how to generate code for plus, what it would really look like is temp1 gets the value 1, y is y. So temp2 gets y plus temp1. And I've kind of shortened that into temp. T1 gets y plus 1. So that's a temp. Then I say param T1. So T1 is the second parameter. Param 0, the constant 0 is the first argument. And these just have the effect of pushing them on the stack or placing them in a register, whatever the calling convention is on the particular architecture. Right? Different architectures may have different parameter passing conventions. Then I call f. So f goes off. This call goes off and does its computation of the function. When it comes back, f has a return value. We know that from the prototype. Since I know that it has a return value, and since I know I'm going to be doing an addition operation, I first grab that return value, and I say retrieve that return value and put it into a temp T2. Now I have the return value in temp T2. Now add 1. This T2 plus 1 is this plus 1 over here. So add 1 and put the result into F. In fact, when we look at the details of how we generate code, there will be more temporaries involved. So what this line will look like is it'll look like temp3 equals 1, something equals temp2 plus temp3, So maybe temp4 equals temp2 plus temp3, and x equals temp4. So it'll be a little bit more complicated. But the general drift of the code is of this sort. Okay? It's going to have this shape. I've just simplified it a little to have it fit on the screen. Okay? At the callee's end, inside of f, we'll enter f, and then there'll be the code for the body of f, and then there's going to be, f has to return a value. So I'm going to say, okay, put the return value into T27 and leave. Deallocate f, clean up, and return. Now, I think in the 3-address code that I have put up for you guys, I think instead of doing it this way, I have return T27, which says take the value that's in T27, put it into the appropriate location, and then jump back. Okay? So same idea, the intermediate code is slightly different. But the sequence of actions that happens at the low level is the same. Okay? So here's how the intermediate code generation is going to work. Here's your syntax tree. Let's first consider the non-void return type. Right? So this is an expression. I have a call. A call has a pointer to f symbol table entry. This is a global entry, right? Global symbol table entry. And I have a list of expressions over here. So this is a list of of syntax trees. Okay? So what does the code structure look like? I evaluate the actuals. So I traverse this list and I evaluate the actuals. And then I have param x sub k, the rightmost, all the way down through param x1. Okay, then I make the call. Then that's followed by retrieve into T0, into some temporary T0. The reason I have a retrieve is that this is an expression. I need the value. Okay, so this is the structure of the code that gets generated. So this is what the code in your compiler looks like. I'm generating a code for an expression. So this is code gen expr for an expression E. The node type in the syntax tree is that it's a function call. So I evaluate the arguments. So code generate expression list, the argument list. And what this does is it traverses this list, spits out code. Then I create a temp for the return e.place. At what location will this expression's value be found at runtime? Create a temp. So I create that temp. That's where I will eventually retrieve the value. That's where I'll take the value of this call. So the code to evaluate E consists of the following. The code to evaluate the arguments that I get from here, and then the param xk through x1, then the call to f, and a retrieve into e.place, which is this new temp. Does that make sense? You don't look convinced, Eric. He just... Sorry, I have to wake you. Just kidding with you. Does this make sense? Do you see what this is doing? Will, does this make sense? Yeah. Okay. So the void case is easy. You don't need to create a place for it. So f has no return value. So that's it. Okay? All right. So now we know how to do code functions. I don't want to talk about reusing temps. So we've done expressions. We've done simple expressions. And what do I need to do? What all is in your first milestone? There is function calls. We take one argument, right? At most one argument. But we know how to do one argument. If I remember, this is the 3-address document. So where's param? Entering, this is how you enter a procedure. This is the code to enter a procedure, right? you save these things, but we don't really need to save the registers. That's so this is all that you need to set up the stack frame for a function. That's how big your stack frame needs to be. What's that? Why is it minus? It's minus because your stack is growing from high to low addresses. You don't look happy about that. Was that your question, Keith? Why is it minus? Yeah. Oh, it's.
No, I was wondering, is the n actually, is that in bytes?
Is n in bytes? Well, at this level, yes, because this is assembly code. So now we're talking to MIPS. Okay, we're speaking MIPSes. So I've generated an enter f at some point. Now I need to actually generate machine code. So what I do is I use a symbol table to figure out how many bytes I need for the stack frame. Okay, what all goes into the stack frame? Let's take a look. Here's what my stack frame looks like. So here's what my stack frame looks like. I have the actuals and so on. So that's part of the callee and so on. I know how many arguments I need. I need 4 bytes for this guy. I know how many arguments I take. Therefore, I know how many bytes I need for them. I need to store the old frame pointer and the old return address. I need 2 words for that. I don't have any saved registers, so this part is 0. I know how many words I need for my locals and temps, right? So that's all I need. So this is how big n is. Okay, so that's how much space I allocate. Yeah?
Really quick question. Is the stack frame word aligned?
Is the stack frame word aligned? Yes, it needs to be word aligned.
So it has to be on 4 bytes?
It has to be on 4 bytes. Now, if I have a whole bunch of chars in here, the chars themselves don't need to be word aligned. But if I have, say, char int, that int needs to be word aligned, so you may have to assign padding. Okay, and that's something that your compiler will do when it's allocating space. Okay? All right. So that's the enter. That's how you enter a function. Yeah, Brian.
It's probably a bad question.
Okay.
The chars don't have to be word aligned, but what if we made them word aligned?
What if you made them word aligned? That would work for scalar chars, but it would not play well with arrays. See, I knew I could I could force you into assigning a single byte for chars. So here's calling a procedure. Here's what a param instruction works out to. Load x into, so here's param x. Load x into a register, store this into that location, and then add this, subtract 4 from stack pointer. So this has the effect of pushing x onto the stack. If it's an array, then I load the starting address of x into register and push the starting address, because arrays are passed by reference. Call, return from a procedure. So this tells you what's going on, and that's nothing terribly weird about that. We are assuming the convention. I think SPIM uses this, and the MIPS uses this rather, that integer return values are returned in register V0. So I load x into V0. Once x has been loaded into V0, I can deallocate the stack frame. I don't really need the stack frame anymore. So I deallocate the stack frame, restore the old frame pointer, and then jump through the return address register. Okay, so I do that. And the retrieve then says, okay, I've just returned from a function call. The return address, the return value must be in V0. Let's save V0 into wherever x is. So store V0 into x, and I'm good to go. Okay? So that's the function calls and returns. Now, that gets you much of the way towards the first milestone, but not all the way. So what we have not talked about for milestone 1, when is milestone 1 due? It's due on November 10th. Okay, so Sam will talk about code generation for simple statements enough to get you to milestone 1. I should be back before then. I think I'll get back on Monday the 8th. And I'll talk about the other constructs that we haven't talked about, statements and so on. And that'll get you going for the rest of the assignment. And if it turns out, if for whatever reason it turns out that I just don't get the stuff covered, then I'll figure out some way to extend the assignment without having it hang over Thanksgiving. But I'll worry about that when I get there. Okay, thanks guys. I'll see you guys in a